So we have seen some special types of elements in a ring. Now I would like to talk about some special types of ideals, and then to tie those two notions together. Already when we discussed irreducible elements, I mentioned how we would also have prime elements, and that notion would come from the notion of prime ideal. Okay, so I want to define for you prime and maximal ideals. So let R be a ring, always commutative with 1 for us, not always in the world, but always for us. So definition, an ideal I in R is maximal. So if I is a proper ideal, that is, I is not allowed to be R, if I is not R, so it's properly contained in R, and it is maximal in the natural sense. So what does that mean? And for every ideal J, which is trying to sit in between I and R, well, it's just faking. So either I is equal to J or J is equal to R. So there's no ideals between I and R. Okay? And the second type of ideal I want to define is prime. So an ideal I in R is prime if, again, we want to exclude the whole ring, and whenever I have A times B in I, a product of two elements, this implies that either the first one is in the ideal or the second one is in the ideal. But this should hold for any AB in R, not AB just in I. Okay, so what are some things we can say about these? Well, so one thing is, what is the relationship between these two concepts? That's given in a lemma, which says that every maximal ideal is prime. Okay. Why is this true? So let M maximal assume A, B is in M, and that A is not in M. Then what we want to show is the other one, B. We want to show that it must be in M. Well, if A is not in M, the reason I'm doing this proof is that it highlights some of the standard techniques in this subject. Because I have an element not in the ideal M, then it's a standard construction to form the ideal generated by A and M. So I can look at the ideal generated by A and M. So this is the smallest ideal in R that contains both M and A. And now what choices do we have for it? Remember what we have here in the definition of maximal ideal. This guy is trying to squeeze in between M. It's generated by A and M, so it certainly contains M. M is contained in this ideal. And this is contained in R. Every ideal of R is contained in R. Now, the fact that A is not in M, that gives us that A is not in M, but A is in the ideal generated by A and M. So that gives us that this first inclusion is a strict inclusion. AM is strictly bigger. Now go back to the definition. This forces that our ideal AM be all of R. This implies, by the maximality, this implies that AM is all of R. But what does that mean? R, we are assuming, has a 1. This means that 1 is in the ideal generated by A and M. Now, every element in the ideal generated by A and M can be written as a sum of some element of R times A plus an element of the ideal M. So 1 is equal to RA plus M for some M in the ideal and R in the ring. Okay. Now, there's one element in the hypotheses that has been lost, and that element is B. So we need to bring it into the picture. We multiply by B, this equation, to get B equals RAB plus MB. Notice that I'm no longer worrying about whether I'm putting, or, well, here we can think of this as multiplying B on the right, but it doesn't matter because the ring is commutative. And now the point is that this element RAB, well, we assumed AB was in M, so RAB, this is in M. MB, because M is an ideal, this is in M. And so this implies that B is in M, which is what we wanted to show. Okay? So the converse of the lemma that we've just seen is not true. Okay? So there are many reasons for this. One is, we have the following lemma. R is an integral domain if and only if the zero ideal is prime. So this is also starting to relate the property of the ideal being prime to properties of the ring, like whether the ring is an integral domain. Okay. Now, another lemma that is, this one is easy and the second one is easy as well, is that R is a field if and only if the only ideals in R are the zero ideal and all of R. So if R is an integral domain which is not a field, then 0 is a prime ideal that is not maximal. Because, of course, the zero ideal is contained in every ideal. So as long as we know that it is prime and that there is some other ideal out there, 0 is contained in it, so it's not maximal. And if we want to be more specific, what is a nice ring which is an integral domain but not a field? So, for example, f bracket x is such a ring for any field f. Okay? So this is a kind of trivial reason for which the converse fails, but we can still ask ourselves, is it true that every non-zero prime ideal is maximal? And that also fails. So question, is every non-zero prime ideal maximal? So this also fails. In general, no. But we will see that for special rings, this does hold. So, but we'll see later this holds in special rings. Okay? Which this will in fact be one of the motivations for studying special classes of rings. We might want to look for rings in which we have this property that every non-zero prime ideal is maximal. But what is an example of a ring with a non-zero prime ideal that is not maximal? So we can take R to be f bracket xy. So here f is a field. R is the polynomial ring over f in two variables. I take the ideal I to be the ideal generated by x. And I have strict inclusions. 0 is strictly contained in x, is strictly contained in the ideal generated by x and y, is strictly contained in R. And now the ideal generated by x, in fact, the ideal generated by 0, the ideal generated by x, and the ideal generated by xy, these are all prime, but 0 and x are not maximal. This ideal generated by x and y is maximal. Okay. So, yeah, so that's prime ideals and maximal ideals. Now, let's try to relate a bit more these properties of ideals with properties of rings. So that is, we can strengthen a little bit these two lemmas that say integral domain, this corresponds to the ideal being prime, and field, this corresponds to the only ideals being 0 and R. We can strengthen this by passing to quotients and using the isomorphism theorems. So we have the following lemma, which says that, so let R be a ring, I in R an ideal, then first of all, the ideal I is prime if and only if the quotient R mod I is an integral domain, and secondly, I is maximal if and only if the quotient R mod I is a field. So with this lemma, we have a precise characterization of the properties prime and maximal for ideals in terms of the properties integral domain and field for the quotient rings. Okay, so finally, I want to use the new notion that we have introduced of prime ideal to define what it means for an element to be prime. So definition, and for this definition, let me assume R is an integral domain. We say that x in R is prime if x is not equal to 0, and the ideal generated by x is a prime ideal. Okay? So this gives us one more type of element to add to the ones that we've studied before. In particular, remember that for integral domains, I defined what an irreducible element is. This was an element that if you break it up into two pieces, one of the pieces must be a unit. How is this related to prime elements? Well, we have the following easy lemma. In an integral domain, every prime element is irreducible. Okay? Now you can ask, is the converse true? Is every irreducible element prime? Then they would just amount to the same thing, at least in an integral domain. But that's the context in which we have defined them. But caution, the converse is not always true. Okay, what do I mean by it's not always true? I mean that in some rings it is true, but in others it is not. And understanding in which rings it's true and in which is not is very closely related to the problem we had before of understanding when every non-zero prime ideal is maximal as an almost converse to the statement that every maximal ideal is prime. Okay? And so both of these questions are pushing us in the direction of singling out a special class of rings in which we have equivalences for both of these statements. And this will be done in the next lecture by looking at Euclidean domains, principal ideal domains, and unique factorization domains.